Today we have another question surrounding flight mechanics. Now let's read to the following question. Consider a jet-propelled aircraft with the following parameters. The wing area 50 meters square, the wingspan 25 meters, the CDO 0.02, the Oswald factor 0.8, thrust specific fuel consumption 0.65 kilonewton per kilonewton hour, the operational mass MOP 8,005 kg, the maximum takeoff weight of the aircraft 13,000 kg. Now, the aircraft has to deliver a payload by airdrop from the airport at location A to B. The distance between the location A and B is 2,000 km. The mission consists of three phases. 1. Climb from the airport at location A to 10,000 meter altitude with a density of 0.41 kg per meter cube. 2. Cruise to location B. 3. Cruise at the same altitude back to location A. The payload is dropped by parachute at location B from the altitude of 10,000 meters. Ignore the descent phase at the end of the mission. The fuel consumed during the climb phase, MFC, equals 500 kg, and the distance covered during the climb phase is 100 km. Now, calculate the maximum payload that can be delivered by airdrop to location B. Once again, calculate the maximum payload that can be delivered by airdrop to location B. Now, first of all, let's draw out all the parameters for the jet-propelled aircraft. Today we have a jet aircraft with a wing size 50 meters square, the span of the wing 25 meters, with the CDO 0.02, the Oswald factor 0.8, the TSFC 0.65, the MOP, which is the operational mass of the aircraft, 8,500 kg, and the maximum takeoff weight of the aircraft, 13,000 kg. The range between airport A and B, 2,000 km, which equals 2 × 6 meters. The altitude 10,000 meters. The density of the altitude 0.41 kg meter cube. The fuel consumed during the climb, MFC, 500 kilogram. The range, the distance covered during the climb, RC, 100 kilometer, which is 10 to 5 meter. The mass of the payload drop, is what to be found. The aspect ratio of the aircraft equals b square over x, which equals 25 square over 50, which gives us 12.5 aspect ratio. First of all, by using the Breguet range equation, R equals 1 over TSFC AG rho S CLCD to the max, to the product of mass MO M1 root bracket. You can deduce that this section becomes the K factor. So now K becomes 1 over TSFC HG rho S CLCD max. Now how do we find our CL, our CD? Our CL equals pi over 3 E AR CDO, which equals pi 3 times 0.8 times 12.5 times 0.02 our CL equals 0.4577. Also using CD formula, which equals CDO plus CL squared over pi E AR, or which can be expressed as 4 over 3 CDO, which equals 4 over 3 times 0.02 or CD equals 0.02 267. Now we can calculate the K factor from the Breguet equation. K equals 1 over T S F C H G rho S CLCD max, which equals 3,600 over 0.65 8 times 10, which is gravity, over 0.41 times 50 multiplied by 0.4577 over 0.267. K becomes 2.77 10 to 5. Now R A to B equals the range of climb plus K minus maximum takeoff weight minus fuel consumed during the climb minus mass at B. Now we can single out MB in order to find the mass of the aircraft at airport B. So therefore, MB equals M maximum takeoff weight minus mass of curve compared during the climb minus RAB minus RC over K all squared. And this will give us 13,000 minus 500 minus 2, 10 to 6 minus 10 to 5 over 2.77 10 to 5. Our MB eventually becomes 1101.28 kilogram. Now, by calculating the range, the maximum payload, we can find out by using the formula RBA, that is they travel from airport B to A. Distance equals K MB minus payload minus MOP then we can single out the maximum payload. So maximum payload to be dropped by the aircraft equals MB minus RBA over K plus operational mass. It can be, and this become minus 2 10 to 6 over 2.77 10 to 5 plus 8,500 all squared. Maximum payload becomes which is the maximum payload of the aircraft. Thank you for staying tuned.